So I'll get started, and then if anybody else is joining us, then obviously they can be here in the next however many minutes. So I shall just start by welcoming everyone again, and especially if you're joining us for the first time. This is the second of our 11 sessions on soil contamination and remediation, and I hope you're going to find these stimulating as well as enjoyable. I know there were some problems with sound and webcams last week, but I trust that is all now working well. As for last week, I will be introducing the lecture, and afterwards we will have a question and answer session. This will be followed by discussion that will be led by Dr. Hui Dang from Trent University, and perhaps you may wish to share your own research interest in arsenic and identify some common themes. You can use the chat option to send messages and questions. You can also speak directly if you have a microphone. So I hope that everyone is now online and ready to start. I can see there's at least 14 people logged on at the moment. If we're ready to go, then it's now my pleasure to introduce Professor Lena Ma, who's the Professor of Soil and Water Science at both the University of Florida and Nanjing University. Her research interests include biogeochemistry of contaminants in soil, water, plant, and microbial ecosystems, and also the phytoremediation and chemical remediation of contaminants in water, soil and waste. And she has 6 patents on remediation technology. She is a fellow of the American Association of the Advancement of Science and also several other societies, and she has received a Discovery Award from the Royal Geographical Society. She has published more than 170 papers and is on the editorial board for several journals, including Chemosphere and Environmental Science and Technology. Today, she's going to be focusing on arsenic, an element which continues to attract a significant amount of attention because of its detrimental effects on human health. And I'll now pass you over to her to tell you more about this.
Thanks, Margaret, for the long introduction. Anyway, hi everyone. I don't know, some is morning, some evening, and noon. So for today, I will talk about background concentrations of trace metals in Florida soil. The focus will be on arsenic, but we did other metals, so I just put this title. If you have any questions, burning questions, you can stop me during my presentation. So what I'm gonna do, this is my outline. I will try to tell people what I, tell them. So the first part, I'll talk a little bit about the background concentration in terms of definition. So what is background concentration? And second, and also it is unclear like how we could express it. There are different ways to, express background concentration. The second part I'll talk about is the background concentrations of trace metal in Florida soil. We had 2 major projects. So the first one is we deal with agriculture soil, and then later on we did another project, urban soil. So I'll share with you how we did it and also the data we have. Again, we have focused on arsenic, and I'll share a little bit about other metals. So that's the plan for today. Now, back like almost 20 years ago, this website called IIES, I think it's called Association for Environmental Health, and used to be soil, and then they changed something else. But anyway, so they have been publishing this survey, try to figure out the soil cleanup goal, what is in different state. So in the US, the regulation, we have a federal regulation, but on a state basis, every state has their own. So I just picked this 98. They did for 5 years, I think until 2003, something like that. So if you look at here, it's kind of interesting, again, on arsenic, and this CO means Colorado, I hope. This is Ohio, Florida, is different state. And for soil cleanup level, you can either use background concentrations, or you can use this called risk-based cleanup level. CG means cleanup goal. So there are either for residential use, so there's one number, or it is for industrial use, it's another number. So if you look at here, I'll just take, Florida. For example, the background concentration in this survey is as 0 to 3 ppm. And the risk-based soil cleanup target level for residential soil is 2.1, and then for the industrial soil is 12. Now, let's move to the right, look at Montana. So their background concentration is 0 to 100, but look at their risk-based number. When I taught this class, I would tell students, I don't really understand. Florida is 2.1. Then Montana is 250, so it's tough. We're talking about 100 times difference. Anyway, so that's how the regulation is done in the state. So we'll go back to Florida. So why we are interested in the background concentration? If you look at a number, so the background concentration kind of overlap with the residential soil cleanup level, right? So that's why it's important, to know the background concentration to, I always say for two purposes. One, you try to determine how clean the soil is clean. That's for remediation. On the other side, is how dirty is dirty when you have contamination issue. So it's important to know the background concentration. So this is a survey. Now, So in terms of background concentration, EPA has a publication, I put it here. They published 95, and it's free, so you can download from their website. They talk about the definition. The first one I want to introduce you is called a natural background concentration. That means it's ambient concentration of chemicals in soil with no human influence. There's no such a thing, right? You can be in Arctic, any remote area, there is human rich, has human influence. So what we talk about actually is this called anthropogenic background, okay? Anthropogenic background is, widely distributed chemicals in the environment, but the source is non-point source, okay? So you cannot have a point source. That is what we try to do. We try to understand what is the background concentration in the environment we are encountered on a daily basis. So this is the anthropogenic background. Now, when we deal with remediation, here's another term, it's called site-specific background. Remember, you can clean up the site to the background concentration, so you need to know the site-specific background concentration. So in this case, it is, distinguish site-related contamination versus, non-site related or, non-point source. So that is the background information. So for our research, we working on the anthropogenic background, not necessarily the site-specific. But here is the kind of the another look. So when you try to do site-specific background, you can't take from the site, right? You have to take a sample off the site. Hopefully the site is similar, in, property, in soil property and not far away. And this is the, anthropogenic, background. And then here is the, site information. So if the site is not contaminated, right, then you have this being 0. So that is the site-specific information, and I'm not talking about this part in this class, okay? So that's the definition. Now, the second part is background concentration, what it is, how are we gonna express it? There are, many ways. The easiest, and the one that's probably most familiar to all of you, is mean, right? The average. You take a bunch of sample and you'll, take the mean. So if you look at this, this is on the y-axis is your sample number, and then this on the x-axis is concentration. This is not really for arsenic, but I just borrow it and to make a point. So the most common one, if you read literature, it is the mean concentration. Now, for US EPA, they actually use another term they call the UCL, so the upper confidence limits of the mean. So they try to make it, I don't know, a bit of wider range. Okay, so that's has been used in the regulation a lot. That's one. And now, if you look at the literature, you know, in the a lot of people actually use 95th percentile. So what that means is you have a distribution and you calculate, okay, based on stats, the 95th percentile. If I translate it literally, basically with your, you know, database, you throw away the 5%, the highest one. They are probably outliers. So that's what's the 95th percentile. Now, if you look at this hypothetical example, so this is, as I said, I just borrowed this. So don't pay attention to the number because it doesn't apply to Florida. So the mean is, for this example, okay, the mean concentration is 15. And so I show here is when you use mean to express, what happened is that you have almost half of your data is above and half below, right? So if I use 15 as the cutoff, my population, half is above it. That's the implication when you use mean. Now, the UCL, say for example, you use you know, 95th you know, confidence level, you can calculate the UCL. I just made this up. I just use this number. Okay, just make it a little higher than mean. So this time you actually exclude 45%. Okay, that means 45% of your number is above this UCL. Okay, it's just approximate. Just give you some idea. Then if you look at a 95th percentile, the concentration becomes 27.5. I made this up, okay? And then you're actually throwing away the 5%. And there's another one, actually 97.5 percentile. This actually is being used in the literature. I think in Washington State, they use this as, you know, background concentration. This means you throw away 2.5%, okay? So this is a different way you can use to do background concentration. Now, I just put it on different slides. So for mean concentration, you can use arithmetic mean or geometric mean. So if it is normal distribution, you can use arithmetic. But if it's not normal, you have to do log transformation, then you're going to use geometric mean. If you read literature, people don't really say what mean. So you probably assume it's arithmetic mean. That's the mean. And then you can use, you know, UCL. That's more for, you know, like regulatory purposes. Or you can use 95th percentile or 97.5. Now, if you look at this last one, in our publication, we actually, we use this. So there is a term. This is called baseline concentration. So that's correspond to the 97.5 percentile. So that's the, I guess, introduction about the background concentrations. So I will go to the two examples, the two studies we did. So the first one, we actually focused on agricultural soil. What I have here is 3 publications. The first one, before I did the agriculture study and the bourbon study, when I first came to UF, I find they have a bunch of soil laying there. So I just, they actually did a phosphorus study. So I just borrowed those soil sample and did this study, the first one, the publication in '97. So we did a concentration distribution of 11 elements in the floor. So this is kind of like preliminary study. So this is one publication. And then this second one is about the agricultural soil. And the third one is, the urban soil. Actually, we have about 10 publications. I only picked 3. So this is the reference. So if you are interested, you can go back to those publications. So the first one about the agriculture soil, it is kind of interesting. When I came here, I realized that our department, we have 8,000 plus archived samples from soil survey. And so they are available and they're free. So when I sent this proposal in, and it's got funded, so I was able to work on this. We were able to do 400 some samples. We can't do the 8,000. And if you look at here, those samples were collected back in the 1967, 89. So that's what archive sample. And for this project, they are only interested in surface soil. So we pick surface soil. And among these 500 samples, there are more than half, they are undisturbed. That means the site, they have native vegetation, no disturbance. And those dispersed soil can be agricultural soil, can be forestry soil. So we were able to select from this 8,000 plus and narrow down to 445. What we try to do is we want to make sure the sample, they are geographically representative. So they are all over Florida. That's number one. And number two, they actually represent all soil types we have in Florida. We have 67 counties. So if you look at it, we only have sample from 51, so 80% coverage. During the survey, in the poorest county, they can't contribute money, so they didn't get their soil sampled. So that's how it get done. Now later on, and the funding dried up, so they didn't finish. So they just did 51 county. And in Florida, we have 7 soil odors. And I guess for some of you probably don't really know what it is. But anyway, so that's a soil type. If you look at it, probably most of you know where Florida is, just in case you don't know. Beautiful Florida is in the southeast US, the very southeast US. So the reason I kind of use this map, I also want to point out, so if you look at Florida, it is coastal state. Okay, so 3 sides is either Atlantic Ocean or Gulf of Mexico. So the very long coastline. And it has implication, you will know later on. So this is the Florida map. As I mentioned, we try to, if you look at the black dots, those are the sampling point we have. So you can see they scattered all over Florida, right? From Panhandle area all the way to Miami and the Key area. And if you look at this is the 7 major soil odors. So if you're not familiar with their soil type, so we try to have a good representation of different types of soil and different location. And here, I also marked Gainesville. That's where University of Florida is at. And also we actually take sample for urban soil. We also focus on Gainesville and also Miami. I just want you to know Miami, south, and Gainesville is in the north central. So that's where we at. This is the breakdown for the soil type. So what we did is we resample the soil based on their dominance. So if they are more spotted soil, we take more sample from spotted soil. So it's a weighted kind of average. The most dominant one, about 1/3 of Florida soil, is the spotted soil. Those one has subsurface accumulation of humic substances. And we have andesol, very, very young soil. They are basically a bunch of beach sand. I don't have the picture for this class, but anyway, so this is the soil type we have. Now, with soil survey, they also have very good soil characterization. So they did a bunch of analysis, not the trace metals, but others. So here, I want to show you a little bit. First, in terms of pH, because Florida is southeast, a lot of precipitation. So the soil pH tend to be acidic. So the most, I'll say 90% will be 4.5 to 5.5. That's the typical soil pH range. And if you look at organic carbon, just don't pay attention to the first two, because they are like a minority. Histosol and mollisol, they have a high organic matter. But the majority of Florida soil, if you look at the bottom, the carbon is like, 1 to 2% organic carbon, very low in organic carbon. That's Florida soil. And the other thing I want you to pay attention, look at the clay content. Clay content is less than 5%. So if you pick a soil in Florida, okay, 90% of the time, it's a basic sand. It's really, 80 to 90% of soil is made of sand. Okay, Florida, that's why I say, we have this coastline. The parent material is marine sediment, so there are a lot of sand. Very little organic matter, very little clay. And as a result, well, you don't expect high concentrations of like trace metals in the soil compared to, say, other part of the state. So that's the sample characterization. When we did the analysis, this is the method. Actually, there's kind of like interesting story. As a scientist, I did use the fluoric acid to digest the soil to get basically all the metal out. And we actually come up with a term called total. But EPA, actually, they use total recoverable. They use just the hydrochloric acid and nitric acid. So later on, you'll probably see some inconsistency with numbers, because some number is total, use fluoric acid. The publication we have is total. But Florida, the regulation, they interested in the total recoverable. So I have to redo the whole thing. So I have a 2-set number, and I didn't make it. I just kind of use it. So if you see inconsistency, it's not because I'm making the data up. It's just two different data set. I didn't talk about that much. So to be used as a database, we have to follow good QA/QC. We have to make sure the precision, accuracy are acceptable. So this database actually, I think is one of the best we have in the country, because we have to follow the EPA protocol. So this is the publication we have. As I mentioned, we did 15 trace elements, and this particular data is based on the hydrofluoric acid, the EPA method 3052, the total digestion. So this is the arsenic number, and if you look at this is the sample, the range is 0.01. So there are a lot of samples. We don't really have a beach sand, right? We don't really have much anything, but, and that's kind of interesting, the higher one has 50. And this is the median, arithmetic mean, and geometric mean. So what I want to show you is the data distribution. So if you look at here, this is the distribution. On the x-axis is the soil concentration, y is the sample. So you probably can tell this doesn't look like a normal distribution, right? It's a skewed. You have a lot of low number on the lower side. So if you look at here, about 90% of the sample we have is the arsenic concentration is below 3.5, very low, majority. And then you have, about another 9%, they're above 3.5. Now I put in the bottom, in Florida, I showed you in the very beginning, you may kind of forget. So for residential soil, for arsenic, it is 2.1 ppm. That's the number everybody follows. For industrial soil, it's 12. And if you think this low, when I came here, the soil for residential is 0.8. So for many, many years, Florida has a 0.8 ppm as a residential soil cleanup. It's really interesting that it's lower than the background concentration. So that's why at that time they are so interested in this data. So what we did is we did a log transformation. So you can see now it is normally distributed. That means if you try to express the mean concentration for trace metals on a large basis, you need to use geometric mean. That's more representative of your data set. So that's the distribution. Now, what I want to show you is kind of give you some perspective in terms of the background concentration and the cleanup level. So for this particular case, if you look at the median, the definition is median is half above, half below. So it's 0.21. So it's very low, 0.21 ppm. Now, if you look at the geometric mean, there's a 0.27. And if you look at arithmetic mean, it's 0.8. So there is a difference if you use geometric mean or you use arithmetic mean, 0.27 versus 0.8. And remember, there's another way to express the background concentration. That's 95th percentile. That is 3.54. That's this distribution. So you can see there are some samples, like this is archive sample. So they are probably the cleaner sample because they were collected back in the 60s, 70s. So the number probably going to be higher if we do it again. But there are higher numbers. So if we look at those samples we have, the range, this is, you can see this range is a little different from the other one. This is 61 because it's a different method. And this is the geometric mean and arithmetic mean. And this is the 95th percentile. So for the longest time, I was trying to convince the Florida EPA, the state, to use this as a yardstick. So if you have a sample lower than 3.5, don't worry too much. But they didn't. They still stick with the 2.1 ppm, 12 ppm. And after that time, that's almost 20 years ago, I learned I wouldn't argue with those regulators. They have their own mindset. So this is the number compared to other part of the world. I couldn't remember where I got those numbers. But anyway, so you can see for Florida, if we use geometric mean, the arsenic number is really, really low. And there's a reason, right? I mentioned because we have beach sand, very little organic matter, very little clay. So there are not a whole lot of stuff in the soil to hold those metals. So we have a low concentration. This is the agriculture soil. Because what we did is we have so many samples. We also kind of try to figure out if there's other interesting trend. So this one, actually, what we're trying to see if the sampling depths will have impact on the arsenic concentration. So what we figured, this is less than 5 centimeter and then 10. So the surface soil did have a little bit higher concentration. You say, well, that's not true. Look at this 76. Well, this is a histosol. So you also move away like mollisol. They tend to have a thicker, depths. So this is, if you compare less than 5, less 10, less 15, then you can see surface soil tend to have higher concentration because they are taking, it's anthropogenic input, right? That's depth. And then the other thing we did is, it's kind of interesting, this one, I don't think we ever published this, even though we put this data together. So we actually pulled all the sample taken from 67 all the way 89. So if you look carefully, right, and you did see a slight decrease in terms of arsenic concentration. Of course, we don't know exactly what's the reason. So for example, it can be sampling, right? Because they were from different locations. It's not from the same county. They from one county to another. And it could be, source reduction, because back in the 60s, right, 70s, we used a lot of arsenic herbicides, pesticides, and then later on those phased out. And it could be instrument, right? So, with time, you have better detection, it goes lower. So, but we did see a trend in terms of, temporal. It goes, not temporal, this is with time. It goes down slightly with time. Another thing we did is we tried to see if all the sample are in the same distribution. And we remember we have disturbed soil versus undisturbed soil, and we did this QQ plot. So if they are all fall in one line, that means they belong to the same distribution. What you see here is undisturbed soil had lower geometric mean, 0.25 versus 0.29. But this again shows you that the anthropogenic input is not that much, only 0.25 to 0.29. So those samples are not, I guess if they have a anthropogenic input, it's not as much. This is the, I guess that time what we did is trying to show you the concentration distribution all over Florida. So the dot size kind of proportional to the concentration. For those green colors, they're pretty much low ones, the green. So if you see yellow, pink, red, they are the higher ones. So as I mentioned, there are higher ones, there are lower ones. What happened is that from DEP, the Florida DEP, they think those are contaminated. There's no way, and the natural conditions, you will have this high number. And so we picked this highest 17 out, and we were trying to figure out, okay, are they contaminated? Are they kind of anthropogenic? They're just what you see in the environment. And we did a bunch of tests, so we can't conclude they are contaminated. We can't conclude they are natural, but based on the information we have, they are most likely is natural. We can't because there isn't that a lot of those sites, they are even undisturbed. So actually what we did is we went back to South Florida, Everglade, I don't know if you know Everglade. That's the most, like a preserved site. They try to make it, undisturbed. So we went there to take samples. If you look at those samples, this is, you see undisturbed site, they have 3-5 ppm of arsenic. So some soils, and especially those calcareous soils, they are from limestone. So they tend to have a higher, concentration. Look at the last one, it's 13 ppm. So anyway, that's what we did with the DEP. They think those numbers are too unrealistically high. They are contaminated, but I don't think they are. But we don't have that conclusive data to show one way or the other. Now, if you remember, I said in the very beginning, I did a small study. So we have 40 soils. So this one actually shows you the depths, because DEP is only interested in the surface soil for contamination remediation purposes, but this is from soil perspective, at a different depths, you have a different number. So for this particular study, we have A horizon, E horizon, and then the BH is where the organic matter accumulation. So if you look at here, surface soil arsenic is 0.2, and the subsurface is 0.5, and this is almost 1. And same thing with autosol, you have 3 ppm, and this is almost 8 ppm. So you can see there's soil difference, different type of soil, you tend to have a different, concentration. Because autosol is in Panhandle area in the North Florida, they have a lot more clay. And the spotosol, they are just a lot more sandy. So you can see the soil type and then the depths impact the arsenic concentration. So if you look at this, what I did is I put the clay concentration, the organic matter, CEC. So you can see at the pH, they have a bit more clay. And here, this one has like 16% clay. So you tend to have a lot more arsenic. So the background concentration of those trace metals are soil dependent. You know, if you have a lot more clay, organic matter, they tend to have higher concentration. So that's the first part for agriculture soil. So this is more based on soil type, different type. But for urban soil, there isn't soil type, right? So we're gonna move to a different strategy for urban soil. So what we did is based on land use. There are commercial areas, for example, restaurant, right? Shopping areas, those, and public area like a library, court, and also residential area where people live. Now, for residential area, it's hard to go to someone's yard. They don't want to dig a hole in their yard. So we try to take some sample from swale. It's a public land and near to residential area. And so based on our research, you know, the two are comparable. So you could take sample from swale area to represent, you know, residential rather than going to their yard. And also like, we also separate the public park versus public building, park. People go to park. And we actually, for this particular project, we did 4 cities. I'll just show you 2, Gainesville, Miami. That's the easiest. And this is the hardworking Tate. So he was my PhD student, and then he stayed for postdoc, and he did this work. I would try to find Ming Chen's picture last night, and couldn't. So anyway, I'll show you just one. This is Gainesville. It's not too clear. So this is the size of Gainesville, about 36 square miles, not 6 by 6, so not too big. And this is the sample we have, 130 samples based on the 4 land use we have earlier I showed you. So this is the arsenic concentration for commercial area. So maybe you can just look at anything above 1. So it has a few in Gainesville. You go to a public building, you also see, you know, those dots above 1 or quite a few above 10. Remember the number is 2.1 for residential and 12 for commercial. And this residential, actually it's kind of good. Residential area, their number are lower. You don't see anything above 10. And then for parks, well, they're good too. Their number are also lower. Only the public building, commercial area, they probably have a lot of what do you call them? During construction, they have brought in a lot of different things. So we don't know what they have on their site, even though they are like beautiful, well sorted, you know, with all the grasses. But underneath, you know, it's kind of unpredictable. So that's the concentration we have. This is just put in, you know, the table. Here, we actually, so if you look at here, this is the mean for commercial area, public park, and the building, and the residential area, and then the swale. So if you look at this number, let me see, if we look at the highest maximum, actually it's not that high. It's only like 6, 3, 6, and 2. So it's good. None actually exceed 12. But if you look at it, they are above the 2.1, right? There are numbers above the soil cleanup level, but not that much. So this is for Gainesville. And so here, what I did is I compare Gainesville versus Miami. And this is kind of interesting. So if you look at Gainesville, there are a few points above the number. And if you look at Miami, Miami is a very different picture. So the pink one is 2.1 ppm for residential, and this one is 12. So in Miami, you see a lot higher number. Gainesville, we don't really have much, right? And now, if I put this side by side, I show this to the DEP, you know, this is what we got, and they didn't do anything. So this is mean number, okay? This is arithmetic mean. We did not use geometric mean. We could do geometric mean, but this is, so for residential area and commercial, park, and public building, so across full land use category, the mean concentration of Miami, the soil, the arsenic number, they are all above 2.1 ppm, all, the mean one. And then look at the residential, it's high, about 5 something. So, but if you look at Gainesville, you know, we're in a university town, small town, it's only like 200,000 people. Miami is like 1 million. So the number is much lower. So you can see, you know, when the city grows, the number is higher, and the small city tend to have a lower number. The reason for it, we also look at the, you know, the soil property. So if you look at Miami, their organic matter is 10, right, 11, and Gainesville is like 2 to 2.5. You may wonder, well, you just said Florida soil don't have a high organic matter. Where did this come from? Well, those like sod, actually they in Miami, they don't really have soil, so they have bringing in a lot of fill materials. So this is not like soil. This is like fill material, and you can tell the pH is very high too, 7. Urban soil, they have a lot of human influence. The pH is higher. In agriculture soil, tend to be like 4.5, 6.5. Look at this in Gainesville, the pH is high, and 5.4 to 7. So that's the reason why Miami tend to have a much higher background concentration than, you know, Gainesville. That's the data I have. And during this study, we also tried a lot of different things. I just want to show you a little bit, like how depths, you know, when you take a background concentration samples, you can sample at a different depths. So this one, we tried 10 centimeter, 10 to 20, and all the way to 60. Now, this is urban soil. There's no A horizon, B horizon, okay? So disturbed soil. So you can see that if you take surface sample, 0.1, 0.2, they tend to have higher concentration than, you know, the subsurface. This is different from the urban, agriculture soil, because they are less disturbed. This is like completely disturbed. So this is, I just gonna show you this. And that's pretty much what I have for today. Then this is the 3 publications I used. And I use this as a, I guess, I don't know, advertisement for my next lecture. This is all the Terrace Batata, the phytoremediation class. I will talk, I don't know, a week or 2 later. All right, thank you.
Thank you very much. That's a really interesting lecture, and thanks for showing us these extensive data sets. It's extremely valuable to have these soils going back a number of years, as well as the more recent studies. Does MD want to start off with questions? Just shout in or type in.
Oh, I don't see anything. Okay, so I need to stop sharing, right?
Yes, that would be good.
Okay.
I don't see any questions that have been typed in. So I'll just perhaps start with a couple of questions myself. I was interested in the depth ranges that you were showing at the beginning, which the soils had been collected over 0 to 76 centimeters, and then you discussed the importance of looking at the different depths in terms of the levels of contamination and how that varies between the agricultural and the urban environments. Now, I know that some organisations have very specific ways of collecting soils. I know, for example, I've been involved with the British Geological Survey, and they only collect from 5 to 20 centimetres, and they classify that as topsoil. Do you have any thoughts as to standard procedures that should be adopted? Or do you think that soil profiles really need to be included to get the full picture of arsenic contamination in different environments?
Well, that's a $64,000 question. Yeah, I think we have to put, I guess, what do you call it? Look at things in a two different way. So the first study, because we had the soil, it is sampled that way, right?
Mm-hmm.
So
Yes.
we follow that. That's not like we did it. We have to follow that, and that's that. And then for the urban soil, when we actually try to do the sampling, and we did that, we trying to figure out we take 5 centimeter, it's probably higher, or 10 or 20. And so after we did that test, and we look at the anthropogenic impact, right? So for human impact, I'm sorry, and anthropogenic impact, they are both surface related, right? Mm-hmm. So people are exposed, yeah. So I think it probably makes sense if we take top 20 centimeter.
Yes.
That's and in Florida, the surface soil, they define it 2 feet. So that's 60 centimeter. But we didn't, for that particular study, because it's preset. So we only, select the surface soil. But they define surface as 60 centimeter. So when you take sample, you have to work with the local regulatory agency, right? They they have to accept your number. Yeah.
Yes, and when you were talking about disturbed and undisturbed in terms of the agricultural context, is that referring to agricultural soils that have been subject to tilling? Are they the disturbed ones?
No, actually it's undisturbed means native vegetation. There's nothing going on. Right. Native vegetation. Disturbed means you're growing something else, right?
Yes.
Yeah, with human. Well, I think undisturbed still have human influence.
Yes.
But the vegetation is still there. At least the vegetation is not, it's I guess they did not grow different things yet.
Yeah, thank you.
Professor, I do have a question, please. Thank you for your talk. You have shown that arsenic could be accumulated with clay and organic matter, but arsenic is shown as well to have a lot of affinity to iron oxyhydroxide. Do you have any information about that, please?
Yeah, that's a good question. It's very interesting if you read the paper, published 99, the one Chen et al.
Yep.
So we try to figure out what is the dominant impact, right? So we have all the parameters. We try to do correlation. The only one that has any correlation is iron. You're right. It is iron. Iron is highly associated with arsenic. But, like organic matter, clay, when we did the 400, all the samples, we try to do correlation. The only one is significant is iron. Yeah, you're right. But for this, I didn't show that. I only showed the organic matter and clay, the general property.
Yeah. Thank you.
And do you find that the organic matter and the iron oxides tend to be intimately associated? Because that's certainly what we've been finding in recent times. If we do size exclusion, for example, and we mobilize the organics, the iron comes through with it. And it's always a question of where is the contaminant? Is it directly bound to the organic matter, or is it the iron which is intimately associated with that organic fraction?
Wow. Well, I guess that's like almost 20 years ago. So we didn't. But because the only thing that's highly associated with arsenic is iron. So we figure the iron organic matter may not, if they are together, then you would also, see some of the organic matter, right, show significant correlation. I think the difficulty in our data set, we have beach sand.
Yes.
So the variation in terms of clay content, in terms of organic matter, is not that much.
Yeah.
When you have a small variation, then, kind of very hard to have a correlation. But strange. But, it's iron still showed significant correlation. So that means arsenic really like iron.
Yes, yes.
Yeah.
And you talked about the importance of quality control, and you showed fantastic data set, your precision and your accuracy and the recoveries. Was that based on certain reference materials that you use, and were you able to metrics match readily with the available certified reference materials?
At that time, there isn't available. We use the certified reference material. We buy those soil samples. They're certified.
Yes.
Yeah.
Yes.
And I guess when you say mattress source, it's not Florida soil. We have to buy. Yeah,
yes.
We don't have certified Florida soil. You can't match the soil texture, right?
Yes. Yeah.
Yeah. That I think certified reference material is accepted.
Oh,
At
yes,
least they are
yes. I just
soil,
wondered.
same matrix. You're not using plant or fish or something
Absolutely.
else.
Yes, I know we struggled when we've been doing work on peat and to try to get a match for the material.
Oh, peat.
Yeah, so
okay.
So I just wondered if you had any thoughts on the importance of trying to do that.
That time they accept. We use the reference material.
Yes,
the soil
yes.
reference material. So we didn't really look into that.
Yeah.
They did have a lot of questions about method. Today I didn't talk about that time. We have EPA 3050, 3050A, 3051, 3052. So we have a paper compared this full method. The 3052 is the hydrofluoric acid. Yeah, the 3050 is just nitric acid.
Yes.
And nitric acid with fluoric acid, with chloric acid, and 3051 is nitric acid. I sometimes I go confused, but it's we had a problem with the method. They care about the method. That's total recoverable, not the hydrofluoric, not the geologist. So scientists they don't like that one.
Yes, yes.
Even though we have a better recovery, you actually get more metals out of soil. They don't want that one.
No.
Yeah.
Yeah. Anyone else want to come in with questions?
I would have one more question, please, Professor Ma. I saw that you have done all this analysis with GFIIS, right?
Right.
Which is awesome because it's just a remark because you have done, I think it's mono elements analysis.
Oh,
right?
Sorry. Yeah. Well, that's a good question. No. We for trace elements, we did use ICP mass.
Okay. Yeah.
Yeah. For all metals. Remember, we have to redo. Okay. So initially, we used the EPA method 3052 that has a hydrofluoric acid. We did all the analysis using ICP mass.
Okay. Yeah.
Then DB says, okay, well, your number is not usable. So you have to redo. So we redid it, but only for arsenic.
Oh, with GFIIS. Okay.
No. When we redo the analysis, when we do the redo the analysis using 3050, just the hydrochloric plus nitric acid, different method. The second time, only arsenic.
Yeah.
One element. That's why we use that's the data I showed you because that's what they are interested. So all the data is based on the total recoverable, the 3050 method, not the 52. Yeah, you're right. Yeah, if we're going to use the GF, the graphite furnace,
it's
it would
be
like
1,000 times of analysis, right?
Yeah,
which is awesome.
ICP mass.
Yeah, awesome. Thank you.
I had a quick question. In the last study, you were looking at the change in arsenic in the urban areas and in the disturbed soil. So I know you don't really have soil horizons with a disturbed soil like that. There did seem to be a little bit of variation with depth, and I was wondering if you could speculate what caused that variation.
So you're talking about the disturbed versus the undisturbed data set.
Mm-hmm.
So the mean for undisturbed, I remember, is 0.25 geometric mean, and then the disturbed is 0.29. Now you're right, because actually they may not comparable because the two data set they have other variables. They are probably taken different time. They have a different sample depths, and they have different type of soils. Yes. So because they are large data set, right? So we assume they are kind of whatever other variable, they are not equal, but they may cancel out. So if I look at that data set, because one is undisturbed, one is disturbed, the geometric mean, one is 0.25, one is 2.9. So I think that disturbed, so the human influence actually increased the arsenic concentration, well, by 0.404 ppm. Yeah, but we don't really know all the variables, hidden there, we don't know.
Fair enough.
Yeah.
Okay, thank you.
Thank you.
So what happens now to soils that are above the limits that have been set in Florida? Is there a program for doing anything about this?
I hope to hear from you I talked to, they don't do anything. And so we also did another study you're probably not familiar, like CCA treated wood. In Florida, we use a lot of arsenic treated wood, and they use that in homes, like staircases, fences, deck. And so one of my students actually did a study, and one of my students live in an apartment, and there's terrace patata growing, right? So we actually went there to take some samples of terrace patata, and then we started to work on those sites. So in a residential area in Gainesville, Florida, because of CCA treated wood, so the arsenic concentration can be 100 ppm. Mm-hmm. They can't do anything either. I asked the toxicologist, they say they don't have a jurisdiction. Mm-hmm. Yeah. So they don't do anything. It's kind of, I don't know. I'm always puzzled. Like you worry about something 2.5 ppm, 2.1 ppm. And here you have like Miami. I showed them that their arsenic, it is higher than 2.1 for sure, almost all of them. And then here in Gainesville, we have a apartment, right, with CCA treated wood. Their concentration like 50, 100 ppm. They don't do anything. So I don't know, in UK, you do anything?
I'm not certain that anything actually happens.
It puzzles me. I don't know, like what you do. It's not, something should be done, but there's no money, right?
No, yes. Yeah.
I don't want to publicize. When we publish this paper, the university want to write a story. And I say, okay, you can write a story, but I'm not going to tell you which apartment it is. They say, you have to put an address. I say, okay, well, we're not going to publish that story. Mm-hmm. Those apartment owners, they are innocent, right? You don't want to get them into trouble, and there's no money to clean up. Yes. It is unfortunate, but that's the case.
Yes, I think it takes a tremendous amount and extreme public pressure to make some things happen. For example, next week when I'm talking about chromium, that is extremely heavily contaminated sites, and it took more than a decade to get something actually starting to happen. So I think there's the money aspect and the pressure coming that actually forces a local authority, for example, to take action. It's a difficult scenario.
It is, yeah. Yes. It's a different country. You have a different, rules and regulations.
That's right. Yes. Yeah. Okay. So, if does anybody else want to ask a further question before I close things off for now? I think that's been a very interesting discussion, and really enjoyed hearing about the different soil types, and also the approach to looking at the background values and why we should use them. So thank you very, very much for your lecture today, and I look forward to the one that you're giving in a few weeks' time as well. Thank you.
Thank you very much. You all have a good day.
Yep, thank you. Okay. So I'll pass over to Hui, and for those of you who wish to continue to discuss and maybe perhaps share what your research is involving, especially if you've been interested in arsenic, then we can do that now. Okay, so I shall now log off. Thank you.
Thank you very much.
All right.
Bye-bye.
Thank you.
Thank you.
Log off too. Okay.